Okay. Uh, okay. So if you get x omega, you will get this kind of sequence, this kind of addition. Okay. So this independent variable is omega. Okay. And if you consider this signal, so this is the frequency domain signal. No, this is the frequency domain signal. Frequency domain signal. This is the frequency domain signal. Okay. So this frequency domain signal, omega, I told you earlier, omega is not a discrete variable. This is a continuous variable. Okay. That is why if we need to find, inverse Fourier transform of x omega to get xn, we need to have integration within 5 x omega e to the power j omega n d omega. That is why we need to have integration. We can't get a summation. But here, when we convert xn into x omega, we can get the summation. So that means this omega is not discrete variable, it is a continuous variable. Okay. So if a signal time sequence is converted into frequency signal, frequency domain signal, again it will have a continuous time, continuous variable frequency domain signal. So omega is a continuous variable. Okay. So again, when we are going to digital process the signal, if we are see the digital processing of this signal, and if this frequency domain is going to do the processing in digital, again we have a problem. Okay. So that why what we need to do. Okay. We need to sample this x omega. We need to sample this x omega and get some frequency sample. Okay. So this frequency sample we referred as xk. Okay. So if we have a time signal xt, if we sample them, we have a time sample, that is n. So our signal will be xn. Okay. And if we have the frequency x omega, and if we sample this frequency domain signal, we will have frequency sample. These are time sample. Okay. These are time sample. These are time related sample. We will have frequency related sample, that is xk. Okay. So this k is related with frequency. Actually, these are some sample related to frequency. Sample related to frequency. Normally we said frequency sample. Okay. Okay. So actually uh, this frequency domain sampling is represented by the discrete Fourier transform. Okay. So in discrete Fourier transform, we will have the frequency sample. Actually, frequency sample, not omega, not a frequency domain signal, but frequency sample. Again, if we apply the DFT, if we apply the DFT to discrete Fourier transform to the time signal, we will have some frequency domain signal, but these are also, this is frequency domain, this is time domain. This one also discrete variable, this one also will be the discrete variable. So this K are samples, frequency sample. Okay. So that is the idea of DFT. Okay. So once we find the DFT, discrete Fourier transform, we will have some frequency sample, not omega. Okay. So this xk, capital XK represents some frequency sample. Okay. Now it is like this. Okay. So let's say that you have this sample again. You have this sequence. You have this sequence. Okay. So there are n plus 1 values are there. N plus 1 values are there. Okay. If you need to get n plus so if you need to get frequency sample, at least you need to have n+1 frequency sample, no? These are some time sample value. Okay, so related to this time sample, there are n+1. For example, let's say that 10 time sample, 10 time sample, at least you need to have 10 frequency sample. Otherwise, it is not okay. Okay, okay. If you have 10 time sample, at least you need to have 10 frequency sample. Okay, but sometime for if you have 10 time sample, maybe you will have more than 10 frequency sample, no? Okay, it is like this. Okay, the time domain signal is like this. You are getting some sample here. Okay, and frequency domain also signal will be like this. Okay, again you are getting some sample here. Okay, so the sample, at least you need to have some sample. If you get 10 time sample here, you at least you need to get 10 voltage sorry, frequency sample. Okay, but you can increase the number of samples, no? If you get 20 sample, that is not a problem. Maybe when you are reconstructing or analyzing, you can do the analyzing better. Okay, so your analysis, so your regeneration will be much accurate, more accurate. Okay, so what I want to tell you is that, okay, okay, you can get any number of frequency sample. So we called n number of frequency sample, n point DFT. We normally refer this as n point DFT. Okay, that means you can get n frequency sample, frequency sample. Okay, but if your time sequence length is L, okay, this n should be greater than or equal to L. Okay, so this n should be greater than or equal to n. Okay, so if you have 4 time sample, maybe you can get 4 DFT, 4-point DFT. Maybe you can get 6-point DFT. Maybe you can get 8-point DFT. 4-point DFT means you are finding 4 time sample. 6-point DFT means 4 frequency sample. 6-point DFT means you are getting 6 frequency sample. 8-point DFT means you are getting 8 frequency sample. Okay, so we normally refer this as n-point DFT. That means this n refer the frequency sample. Okay, so this n normally should be greater than or equal to the length of time sequence. This L is the length of time sequence. Okay, time sequence. Okay, so that is that. Okay, and so you can see that it is some kind of a frequency domain sampling. Okay, frequency domain sampling, it is referred as discrete Fourier transform. Okay, and this is the normal Fourier transform. Okay, so it show how this Fourier transform will become DFT. Okay, so you no need to, if you need to just check them. Okay, just check them. Okay, but finally what is important is this one. Actually, the important part is this one. Okay, this is what we need. Okay, so here you can see that. Okay, if you can see that if you have xn time sequence signal, okay, xn time sequence signal, okay, xn time sequence signal, then uh, then it should be multiplied by e to the power minus 25 kn divided by n. Okay, Okay, so this n is again the period. Okay, n is again the period, or maybe the number of terms. Okay, number of terms. Sorry. This is n is the um, number of frequency sample. This n is the number of frequency sample, and you need to find this n should be greater than or equal to L. Okay, so that is very important. Okay, so this L, so this n should be greater than or equal to length of the time sequence. Okay, so this n is the frequency number of frequency sample, endpoint DFT. This n is this here. Okay, so if you are asked to find the endpoint DFT, this is n is here. Okay, so J25kn divided by n. So this k will be from 0 to n minus 1. Okay, so this is how we find the DFT. So the summation is there, simple summation is there. Okay, and here you can see that this is the inverse Fourier transform, inverse discrete Fourier transform. That is also very simple. It is also summation. Now you have this frequency sample. You need to multiply it by this one, J25kn divided by n. Again, this simple, and now you need to find this n from 0 to n minus 1. So it will be 0 to n minus 1 again. Okay, so that is the IDFT. Okay, so this is the DFT and this is the IDFT. Okay, quickly we will do one example. Okay, okay. So if I ask you to find okay, find we will get maybe we have examples in the book. Okay, we will get the example from a book. I think it will be easy. Okay, actually DFT also you can get using this matrix also. Okay. So you no need to much pay your attention on properties on DFT. Okay, so same properties are there also, like Fourier transform. Okay, the properties also will be there. Okay. Good question. No, no. Okay, okay. So actually, here you need to apply the convolution property, maybe. Okay, convolution property. Okay. So related with the DFT also the convolution property is there, so you can see that this one. Okay, circular convolution. Okay, so if you get the convolution of two DFT signal, then that will be multiplied. Okay, same properties are there. Okay, and maybe we will try to do this question. I think it will be, where is the question? This one. Okay. Okay, so we will try to do this question. Okay, so the Hn is given. Hn is given. Hn is given as, this is the impulse response of a LTI signal. Okay, LTI system. Okay, Hn is given as 1, 2, 3. Okay, Hn is given as 1, 2, 3. 1, 2, 3. And input signal Xn is given as Xn is given as 1, 2, 2, 1. 1, 2, 2, 1. Okay. 1, 2, 2, 1. Okay, 1, 2, 2, 1. 1, 2, 2, 1. Okay, and so this is the uh, this is the linear time invariant system. Okay, and if you apply Xn, you will have the response related to this Xn, that is Yn. Okay, so response of Xn is Yn, and response of impulse is Hn, that is normally referred as impulse response. Okay, so here impulse response is given, the input signal also given. Okay, so output signal you can calculate using the convolution. You can get Xn convol Hxn. Okay, actually this is a periodic signal, so you can get linear convolution here. Okay, linear convolution you can get, but here it is stated as the circular convolution. No? Oh, no, linear convolution. Okay, so you need to get the linear convolution, because normally for the aperiodic signal sequences we are applying linear convolution. In discrete convolution, there are two types of convolution, linear and circular convolution. So you can apply linear convolution. Okay, so this linear convolution is not much difficult. Okay, I have one recording, I will apply it to you. Then you can see how to find the linear convolution. Okay, linear convolution. Okay, actually the linear convolution maybe also you will get questions. Okay, so you need to familiar with the linear convolution also, but now we are in DFT, no? Okay, so I will not mesh up this with linear convolution. I will give you one example related with the linear convolution, then you can see how to find the linear convolution. This is not much difficult, very easy. If you can, if we did one example, you can see the uh, steps. Okay, in linear convolution it will be not much difficult. Okay, okay, now what I want to tell is that, okay, so if we are asked to find the response with respect to Xn, you can directly get the linear convolution. Actually getting the linear convolution will be easy. Okay, in case of continuous convolution it is somewhat hard. You need to do a very big integration. No, the integration should be position to position. Maybe you have done. Okay, maybe not, I don't know. Okay, but for the discrete time signal, convolution is somewhat easy. Okay, so you can find the convolution here. Okay, but our question said that we need to use DFT and I-DFT. That means they are asked us to use this property. Okay, this property. Okay, so this property, this circular convolution, maybe that is also will be applied to the linear convolution. Okay, this will be circular and linear convolution. Okay, we assume that. Okay, because linear convolution is not there. No? Okay, so definitely it should be same. Okay, okay, so now you need to apply, okay, DFT and I-DFT. So what you need to do? Okay, so what you need to do? So first you need to find the DFT of Hn. You need to find the DFT of Hn. Okay. Then you need to find the DFT of xn. Then you will have some values, then you need to multiply those values. Okay, then if you multiply this hn and xn, DFT of hn xn, let's say that this is hk and this is xk. Okay, so if you multiply it, okay, if you find hk and sk, then you can have hk into xk. So this is the DFT of yk, DFT of yk. Then you can find the yk here. And if you know the yk by applying IDFT, inverse discrete Fourier transform, you can find yn. Okay, so that is why they ask us to apply DFT. So first we need to apply DFT to this one and this one. So it will be hk and xk. Then we can multiply them. So we will have the yk. Yk is the DFT of yn. Okay, then our ultimate goal is find yn. Okay, response xn, the response if the xn is given. Okay, so if we apply the IDFT to yk, we can get yn. Okay, so it is simple. Okay, so we will see how to apply DFT to this one. Okay, then we can see how to apply this equation. Okay. Okay, so you can see that this is the given input signal. Okay, so its length is 4. 1 2 3 4. So you can see that length is 4. So this is the impulse response. It has a length 3. This sequence length is 3. Okay, so it is said that linear, if we get the linear convolution, we will have the length n is 6. Okay, I can't remember it how come. Okay, so I will give you one example, then you can conclude this. Okay, you can understand this how it become n6. Okay, so once we apply the linear convolution, so we will have 6 length value. So okay, so that means yn will be 6 length signal. Okay, the yn will be 6 length signal. Okay, so it is said that the size of the DFT must be at last 6. Okay, so at last we need to find 6-point DFT, 6-point DFT at last. But here they have find F8-point DFT. Okay, they are find 8-point DFT. So it will be much better. Okay, so at least you need to find 6-point, but 8-point DFT is find in here. Okay. Okay, we will see how to find the DFT of Hn. Okay, so first we will take Hn. Okay, first we will take Xn. Okay, we will take Xn. So Xn is 1 2 2 1. This is our signal. Okay, so what is the length of this signal? That is 4. Okay, then at least you need to find 4-point DFT here, 4-point DFT here. Okay, 4-point DFT here. Okay, for example, if we find 4-point DFT, we will find 4-point DFT. Okay, so that is no need to do according to our example, but we will find the 4-point DFT also. Okay, so if we find 4-point DFT, okay, so the DFT will be xk into xn, this n from 0 to n minus 1. Okay, n minus 1 e to the power minus j 25 divided by n kn. Okay, this is the identity for the DFT. This is the identity for DFT. Okay, and it is say that k should be from 0 1 2 so on up to n minus 1. Okay, is that correct? We will check it. Yeah, is that one. This one, no? Okay. So this is xk, n from 0 to n minus 1 xn e to the power minus j 25 kn divided by n. Okay, k from, okay, our one is correct, no? Okay. So okay, xn e to the power minus j 25 kn minus j 25 kn divided by n. So this k should be 0 to 1 to n minus 1. Okay. Now we are asked to find 4-point DFT. Okay, we are asked to find 4-point DFT. That means what? N is equal to 4. N is equal to 4. Okay, that means we are finding at least 4 frequency samples. We are going to find at least 4 frequency samples. 4 frequency samples. Okay, 4 frequency samples. These are the frequency samples. So we need to find 4 xk's. No, 4 xk's we need to find. These are frequency sample. You need to find 4 xk's. That means this k from 0 to n minus 1. That means in our case, this k will be 0, 1, 2, 3. Okay, so we will have 1, 2, 3, 4 frequency samples. That means those are will be x0, x1, x2, x3. We need to find 4 frequency samples, no? 4 frequency samples. Okay, so this is our uh, signal. Okay, and if we get the signal from 0 to n minus 1, this is n. Okay, n from 0 to n minus 1. So that means 0 to n minus 1, 0 to 3. So that will be okay. No, this is 0, 1, 2, 3. All the time sample will be calculated. What happen if this n is less than n? What happen if we choose 3-point DFT? What happen if we get 3-point DFT? That means you are going to do it from 0 to 2. That means you are only counting this one and this one and this one, these 3. So this time sample will be not considered. Okay, so your analysis will not be okay. Okay, so there may be not enough frequency sample. Okay, so at least this n should be greater than the length of this sequence. Okay, okay, so that means if we are finding the minimum DFT n equal 4-point DFT, at least we need to find 4 frequency sample corresponding to this 4 time sample. Okay, there are 4 time sample corresponding to this time sample. We need to find 4 frequency sample. Okay, so now very simple. Okay, so this one also very simple. You can I think now already you can see how what we need to do. Okay, so when k is 0, okay, so you need to find the 0th frequency sample x0. That is, you need to get this summation from 0 to n minus 1, that is 0 to 3 xn e to the power මොකද දැන් okay, minus j 25n kn. Okay, so minus j 25, n is 4, 25 divided by 4, k is 0 now, k is 0, n. Okay, so 0 means e to the power 0, so this will be 1. Okay, so you need to find only this one, so you need to expand this, so you can find simply x0, x1, x2 plus x3. Okay, so this is one frequency sample, that is 1 2 2 1, 1 plus 2 plus x2 is 2, x3 is 1. Okay, So you will have 1, 2, 3, 5, 6. Okay, so this will be 6. This is the zeroth frequency sample, that is 6. Okay, because you are multiply this e to the power minus j, the frequency sample can be complex also. Okay, the frequency value will be maybe sometime can be complex. Okay, so and if we consider when the k is 1, k is equal to 1, again you need to find x1. Okay, that is the value from 0 to 3, xn e to the power minus j to 5 divided by 8. Now k is 1, n. Okay, k is 1. Okay, now you need to expand this again. X0 e to the power n is 0, e to the power 0 plus x1 e to the power minus j to 5 by 8 minus j to 5 by 8, n is 1. Okay, plus x2 e to the power minus j to 5 8. Now n is 2 plus x3 e to the power minus j to 5 8. Now n is 3. Okay, so these are the value. Then you can find this one also. Okay, so x0 is 1 plus x1 is 2 e to the power minus j 5 by 4 plus x2 is again 2 e to the power minus j 5 by 2, because this is 2 and 2. 2 into 2, 4. So it will be 5 by 2 plus x3 is 1 e to the power j 2 5 into 3. So it will be 6 5 divided by 8. Okay. So maybe calculator you can find the uh, complex value here, x plus iy value here using a calculator. Okay, or maybe you can keep this here. Okay, and if you use Euler formula also this 5 by 4 5 by 2, this will be cos 5 by 4 sin 5 by 4. So you can find that term also. Then using Euler formula also you can find the this Cartesian form of the uh, frequency sample. Okay, in the same manner, so you can find x k is 2. Okay, that is the third frequency sample x2. Okay, in the same manner it is also 0 to 2 xn e to the power minus j 258, k is now 2 n. So you need to expand this and find that value. x3 also you can find the last sample, frequency sample, when the k is 3, that is 0 to 3 xn e to the power minus j 258. Now k is 3 n. Then you can expand this from 0 to 3 n from 0 to 3. So here also you can find. Okay, so that is how you find 4-DFT. Okay, then you have xk value. Okay, you have xk value. Xk, 0th xk is 5, not 5 6. And the second one will be a complex number. Third one also will be a complex number. Fifth one also will be a complex number. I can't say this is a complex number. Sometimes it can be real numbers also. Okay, so we will have 4 frequency samples. Okay. What happens if you find 8-DFT for xn? Okay, now you will have 1 2 2 1. This is xn. Now you are going to find 8-DFT. 8-DFT means you need to find 8 frequency sample. So xk will be same manner 0 to some value xn e to the power minus j to 5n. Now n is 8 kn. Okay, now this k, So you need to find 8 frequency sample, no? That means you need to find x0, x1, x2, x3, x4, x5, x6, x7, x8, x7 up to x8. Okay, so that means 1, 2, 3, 4, 5, 6, 7, 8. Okay, 0 to 7. You need to find 8 frequency sample. Okay, that means n is equal to 8. That means n is equal to 8. That means k should be from 0 to 1, 2, 3, 4, 5, 6, n minus 1. So that will be 7. Okay, so you need to find 8 frequency samples. So k will be from 0 to 7. Okay, 0 to 7. Okay, now n is 8. So here also 0 to 7 you need to find. Now you can see that here we have only 0 to 3. Xn, there is no 7, but xn need to n should be from 0 to 7 you need to find. Then what you need to do simply, okay, simply you can add some zeros here. Okay, up to this length is 8. Okay, that means 1, 2, 3, 4, 5, 6, 7, 8. Okay, so you add 4 zeros. Okay, so you add 4 zeros here, 4 zeros. Okay, so we called it zero padding. Okay, we call this zero padding. Okay, so simply you can add some zeros to the end of the sequence. Okay, so that is we referred as zero padding. Okay, now very easily you can find when k is 0, x0 you can find. So xk will be summation from 0 to 7 xn e to the power minus j258. K is 0, so e to the power 0 it will be 1. Okay, so you will have to expand this x0 plus x1 plus x2 plus x3 so on up to x7. Okay, so x0 will be 1, x1 will be 2, x3 will be 2, x2 will be 2, and x3 will be again 1. Others are 0. Others are 4 zeros. Okay, so again you will have here 1. So that is your 0th frequency sample. In the same manner, you can find the first sample, second sample, third, fourth, fifth, sixth, seventh. Like this you can find. Okay, so very simple, you can apply the DFT. Okay, so when you are going to do this, okay, so try to do this one. Okay, try to do this one by yourself. Okay, that questions I show you. Where is that question? This one. Okay. No, here you are asked to find the circular convolution of these two. Okay, so I will explain how to do this. Then you can do this. Okay, I will send you a recorded session. Okay, I have one example. Okay, this is very simple. Okay, actually not simple. The procedure is simple, but there are big thing to do. Okay, you need to do this kind of circle thing. Okay, but it is easy concept is there. You can easily do it. This is example. So what you need to do here, you need to find 8-point DFT. Okay, 8-point DFT of HN. That means you need to 5 zero padding. Add 5 zeros here. Okay, so 8. That k from 0 to 7. Okay, n will be 8. So k will be 0 to 7. So you can find x0, x1 up to x7. Okay, and here we also find the 8 DFT. Okay, 8 DFT, how to find, we see how to find the 8 DFT. Then you can find this 8 DFT and 8 DFT. Then you can multiply them together. So this one also 0, this one also 0. Okay. So you will have, okay. So you will have, it is like this. You will have HK, okay. That is from 0 to, you will have some frequency sample up to 7, 0 to 7, 0, 1, 2, 3, 4, 5, 6, 7. You will have some complex value. Actually, you can't mark them because these are complex value. Some of these will be complex value. Okay, complex value. And once you find xk, okay, 8 DFT of xn, okay, again you will have a 8 point, 0, 1, 2, 3, 4, 5, 6. So okay, these can be complex value. Then what you need to do, you need to multiply this together. That means this one will be multiplied by this one. The one first frequency sample will be multiplied by this frequency sample, first frequency sample, so on. You will have again as yk 8 frequency sample. So you will have y1, y2, y0, y1, y2, y3, y4, y5, y6, y7, like this, 8 frequency sample yk, okay, for yk. Then you need to apply the DFT here, IDFT here. Okay, so IDFT also very simple. That is also you have to apply the you have to apply this summation. Okay, summation. So that is much not big issue. Okay, so try to find the inverse discrete Fourier transform of that one. Okay, uh, okay, so using this identity. Okay, so again you need to get some identity. Okay, here the so again you need to find 8 sample, 8 time sample. Okay, so that means n from 0 to 7. Okay, so k from 0 to 7, you need to find k from 0 to 7, 1 by 8, 0 to 7, this one. Okay, so y0 you have, y1 so you have, y2 you have, y3 you have, so on. You can find yn value also. There should be 8 yn value. Okay, so try to do this one. Okay, I think it will be much difficult. Okay, so we will now conclude this. Okay, I will send you the recorded session. Okay, thank you. Okay. Okay, thank you.